Okay. So my name is Addison Morris. I'll be doing a video on calorimetry. Let me just pull up my PowerPoint here. Okay. Calorimetry. Let's go. So I just want to start out by talking about what is calorimetry. So by definition, it's the measurement of the amount of energy given off by a physical process or a chemical reaction. Kind of a cool breakdown of calorimetry. Dang, dude. Calorie means like energy, like it's like a unit of energy, and metry is measure, to measure. So calorimetry is the measure of energy, or like the energy given off by reactions or physical processes. Some modern uses of calorimetry are like determining the calorie content of foods, and also calculating the energy given off by fuels and determining which one is the most effective, the most efficient, and which produces the least amount of gases and such. So it's still used very much so today. How they measure calorimetry, how they do so is with calorimeters. So there's two types of calorimeters. The first is called the coffee cup calorimeter, as you can see here in this design. So it's like a little cup, and they fill it with they measure the amount of water they put in there, and they have a thermometer. And what they do is they take the unit that they want to, or the material that they want to measure, they place it in boiling water until the whole material is heated up. Then they place it into this cup, and they measure the change in temperature, the delta T, and they use that, plug it into the MCAT equation to determine the heat capacity of certain materials. So yeah, they mainly just use this one for heat capacity. It has some downsides because it lacks, like it's not like a closed system, so you can't really do like an explosion. You can't like burn anything to determine like how much energy is given off. Also, like stuff can spill out, and it's not super safe if you're doing something blowy uppy. So yeah, like I said, not able to burn reactants. So that way they have another type of calorimeter, which is a bomb calorimeter. And so as you can see here, they have a large insulated tank, and inside they fill it with water and another smaller container called the bomb. And in this bomb, they fill it with oxygen, air, and the substance that they want to burn or combust. And so they perform the reaction. And what they do is they have this stir right here, which continually moves the water so that the water in the calorimeter is able to all be equal and not have disproportion based on what is like closer to the bomb. And then they do the same thing to measure the delta T, the change in temperature. And they can use that and based on a couple equations to find the delta H of substance. Yeah, delta H is the energy that's given off from burning or combusting. So, like I said, it requires an explosion. So these are really nice machines. They're a little bit more expensive than the coffee cup calorimeters. And next, I just want to go over some of the equations that are used to apply to each one. So for the coffee calorimeter, like I said, use the MCAT equation. You'll set the MCAT of water equal to the negative MCAT of the burned substance, because what's being burned is giving off energy, so it's negative. The water is receiving energy, so that's why it's positive. And you just fill in all the variables. You will know the mass of the water, you know the heat capacity of water, and you know the delta T of the water based on what is on the thermometer. And then you'll know the mass of the substance that you've heated up and placed in the calorimeter. You're trying to find the heat capacity, and you know the delta T as well. So you just use this equation, find solve for the unknown variable. It's fairly simple. Then for the bomb calorimeter, it has some different equations. So the basic equation is negative Q of the reaction is equal to the heat capacity of the calorimeter times delta T. So basically, you can find how much heat is given off by what is burned in the bomb by timesing the heat capacity calorimeter by the change in temperature. And then because Q is equal to delta H, you can replace that for the delta H of the reaction. Same thing. The heat capacity calorimeter times the change in temperature. And then finally, you can determine the heat capacity calorimeter if you already have a substance that you know it's how much heat can be given off for a combustion. So you can plug that in and you take the amount of heat for how many grams that are or moles that are combusted divided by the delta T, the change in temperature. And you can find the heat capacity of the calorimeter. So let's do some practice equations. So right here, calculate the heat capacity of a calorimeter if the combustion of 4.66 grams of benzoic acid produces an increase in temperature of 7.149 degrees Celsius. When we know that 1 gram of benzoic acid releases 26.38 kilojoules. So just looking right here, we got to find what are we trying to find? We're trying to find the heat capacity calorimeter. So if we look back at our equations, we know that it is this third equation right here that we are trying to find. So we got to look for which ones we have, the heat given off per grams or per moles, and then the delta T as well. So we plug that in. So we have to determine how much heat is given off from that many grams of benzoic acid. So we times the number of grams by the heat released. That should give us 123 kilojoules. And then we go ahead and we plug that into the equation that we have here. So I'll just give you guys a second to do that. So it's fairly simple. Once you've done that, you plug it in, you should get 17.21 kilojoules over degrees Celsius. And that is the heat capacity of the calorimeter, like it's being asked up here. So another practice problem. This very fancy chemical, I'm not going to try to pronounce that, is found in nearly 100 spices and fragrances. So cool, fun facts. I think the important thing here is the chemical makeup, chemical formula of the substance. So the complete combustion of 1.608 grams of the substance in a bomb calorimeter, so the one's enclosed. So we know we're trying to find either delta H, heat capacity calorimeter, or the heat that's given off, or the Q. So we have the heat capacity calorimeter, and produce an increase in temperature of 19.35 degrees Celsius. We already know the delta T. So how much thermal energy is produced during the complete combustion of cymene? So we're going to use this equation. The negative Q of the reaction is equal to the heat capacity calorimeter times the change in temperature. And then we find out how much energy is emitted by the combustion. Let's go ahead and plug that in. It'll be 3.640 times 19.35. Just kind of side note, in all these equations with calorimeters, the temperature will always be in Celsius, or what is given most commonly. You guys a second to do that. So you guys should have gotten a 70.43 kilojoules negative, because it's being emitted, it's leaving the substance. Yeah. One last one. So this flavor of anise is due to anthanol. I need to have a pronunciation guide. A compound with molecular formula of C10H12O. Combustion of 1 mole of this product produces 5,541 kilojoules of thermal energy. That's pretty big. So if you were to burn 0.95 grams of ethanol in a bomb calorimeter whose heat capacity is given, what is the change in temperature? So this one, we take that initial equation. Let's go back up to it. So we have it right here. So take this initial equation, we're just going to flip it around, and we'll take delta T is equal to the heat capacity calorimeter over the energy that is given off. So first we got to figure out how much energy is given off. So we know how much for 1 mole, but we don't have 1 mole, we have 1 gram. So we have to plug that in. So we take the grams and we divide it by the molecular weight. And then we times it by a negative 5,541 kilojoules. Negative because it is being given off. We're trying to figure out how much was given off, or how many kilojoules were given off by that many grams. Give you a second to do that. Okay. So you should have gone negative 35.5. So remember, we took the 0.95 grams divided by the molecular mass of ethanol. I think it was like, this really is like 120 something. And then we times it by negative 5,541. And then we plug it into this equation right here. So delta T is equal to, oh, whoopsies. I did that. Oh, I said it wrong. Yeah, no, this is how it should be. My bad. So plug the numbers into delta T is equal to negative delta H. So what we just got here, negative 35.5, and we divide it by the heat capacity calorimeter. So 7.854 kilojoules per degree Celsius. So you guys go ahead and plug that in. Okay, so you should have got 4.52 degrees Celsius. And that is the change in temperature in the calorimeter. So that's all I have for you today. Wow, I'm sounding like Dr. Martinson. Let's go. Sweet, I'm already a professor. So yeah, just reminder, calorimetry is the measure of energy given off from reactions. So very basic definition. 2 types. One, the coffee cup, which is used to determine the heat capacity. And then the bomb calorimeter, which is used to determine delta H, or how much heat is given off. And also heat capacity of calorimeter can be determined through that, as well as delta H if we know the other variables. So in this class, it'll probably give us all the other variables and not what we really want, obviously. And then the equations for the coffee cup calorimeter, the MCAT, set one equal to the other. Bomb calorimeter, we have the Q reaction is equal to heat capacity calorimeter times delta T. And the rest of them are just kind of like different variations of that. Just got to think it through correctly, not like I did earlier. And yeah, that's it. Thank you so much for watching.